All right, so let's continue. So we saw how we can solve this scheduling problem by using this heuristic, this greedy choice property of choosing the finishing time first. And again, now, of course, the question is now, how in the world would you prove this, right? Well, it turns out again, so how in general, right? How in general do you prove this type of optimal? Well, the original material said, left as an exercise to the reader, meaning that's you, right? But I'm not going to make you do it in the class. It's very easy for professors to say, okay, yeah, let the student do the work actually, right? Here the hint is use proof by contradiction. So use some, not use a greedy algorithm, not use the last finishing time first and prove that this actually leads to suboptimal choice, right? But the in general way of proving it is you use or old friend induction, right? You basically have some base case, right? You prove that it's optimal for small case and show that it's going to bigger and bigger cases. This will always lead to the optimal solution, right? But again, proving in general it's pretty hard, right? Depending on the problem, right? So that's one issue, right? But again, the takeaway is it's easy to come up with this greedy approach, right? And then from then on you can go through and find something to work with, basically. Now, yeah. So how should your smell test? What should be the smell that there might be a greedy solution, right? First of all, this problem should be easily decomposable, right, in smaller subsets of the same problem. And it seems like if you see that at each stage, right, at each stage of the problem, right, the optimal solution stays the same, right? That if it's like, okay, you have a bigger problem, if you find some solution, you break down the smaller problem at the smaller problem stage, the approach stays the same, then of course that will lead to a possibility of a greedy approach, right? Okay, so now it turns out, so now you take a different problem, a same scheduling problem, but maximize the length of schedule. It's not only, you don't want to see the most lecturers, but you want to spend the most time sitting in a lecture, right? Very dubious choice, right? For optimization, right? But let's assume you want to do that. You want to spend the most day in the lectures. So again, what do? This is a little bit different. It turns out that there's no real greedy approach for this, right? To maximize, right? Meaning we need to, so whenever you need to look beyond the horizon of the greedy approach, that implies that the greedy approach is not optimal. So what does it mean here, right? It means you have to calculate something else, right? You need to use you need to store some state, you need to store some information, right? On this, in here, you would use something called dynamic programming, which we will use in which lecture? Let me see what lecture I'm going to use that. We're going to use it in about next week or the week after. No, actually next lecture, so next Tuesday, we will look at dynamic programming where we store some state, we store some information basically, right? So, either top down or bottom up, but we'll see about that. Now, so, greedy approach will give us, again, your main takeaway for today is it could be a good first step, right? And after that, you can see, okay, maybe this is, okay. If you find a counter example, maybe it's not so great, right? So, so greedy approach, right? If you see maybe again possibility of a global minima, right? So let's look at another famous problem. So famous, actually, a series of problems called knapsack problems, right? Or backpack problems. You are, you are a smuggler. You are just returning, or actually common problem. You're going back from a foreign trip, and you're trying to buy up the best goodies to bring home, right? So it's a called combinatorial optimization problem, right? So a rucksack or backpack or some sort of suitcase, right, or a container, right? So you want to fill it out with the most value, right? But of course these items have weight, right? they have weight, right? And they have, and they have, a value per pound, right? So there's, 15 kilos in this case, right? That's, I think I can call it 15 kilos, right? But that's, of course, not Air Baltic, you don't. You can't carry 15 kilos, right? 8 kilos, right? Or well, 10 kilos. So, and you have these, costs $4, right? Or €4 if you want, and 12 kilos. That's probably not what you want to take, right? You probably want to take this box, right? $10 and 4 kilos, right? But the problem in this case is, of course, there are multiple variations of this problem, and there are some problems where the greedy approach will work for this knapsack problem, and there are some sub-problems of this where the greedy approach will not give you the best solution, right? So, okay, let's assume the called 0-1 knapsack, right? Yeah, maybe simplest variation, meaning you can either take the item or you cannot take it, right? You either leave it behind, buy it or not buy it, right? You have your you're in a store, like, I don't know, duty-free store in the airport, and you haven't bought anything, right? And you just want to bring the most bang for the buck back, right? So, now, right, and formally it can be defined as you have some items, you have some weights, and you have some values, right? Yeah. But you can only take one or nothing, right? So, of course, you have to check n items, right, weight, right? So, you have 3 items, they weigh 20, 50, and 30, right? Values are 60, 100, 120, knapsack has capacity of 50, right? Extremely simple example, right? Very simple example. How would you solve this? Right? First of all, what's the optimal solution? So, first of all, what should you look for? First of all, what should be your rule? Well, do you want to get the heaviest one first? Do you want to get is that a good rule?
Can you introduce like a price to weight ratio?
Yes, of course. Of course, you want like when you go to a supermarket, right? By law in Latvia, in Europe, you have to have the price per kilogram, right? So that's what you calculate, right? So you look, that would be a good rule for use for a greedy approach, right? So, will we see, is this going to work for O1, right? Problem, let's take a look, right? So we have this O1 problem. So indeed, that's the introduced value by weight, right? So this is best bang for buck, because you don't want to take this heavy 12 kilos, which only costs $4. I mean, that'd be stupid, right? Right? I mean, unless it's something you really know your friend really wants. I don't know what could that be. That's pretty cheap for 12 kilos. What the heck could that be? Actually, I don't know. Like salt or something. I don't know. €4 for 12 kilos or something. Sand, maybe sand. Yeah, you bring sand, maybe. Yeah, probably. Okay, but you don't want that, right? You want something. You want these boxes many, right? You only can take one. That's the problem, right? So you can take this one. Well, in this particular case, you have 15 kilos, right? You basically take 1, 2, 3, 4. You can have all of these, and don't leave this one home. Don't leave this one in the airport. Okay, but yeah. So in this particular example, we have 20 weight, 50 weight, 30 weight, value 60, 100, 120, right? And capacity 50, right? So obviously, we don't want to take the most weight, right? Because we have some, in this particular case, right? We have a nice solution of taking the first and third, and we skip the second one, right? Right, so, knapsack 0-1. We have capacity, weights, values. One thing I would probably, if I had time, I would like to rewrite this some point. I don't like the fact that it's actually, as far as programming goes, right? We have these weights, values, and capacity, right? And the weights and values are sort of like in a separate lists and array, list structures. They probably should be better stored in like an object, class-based approach. But okay, let that be. Let that stay for now. I'll maybe add rewrite using item objects which have weights and values in them. Okay, but okay, right. values as properties. Properties attribute. Yeah, but okay. Now, weights and values again. So we value by weight, right? For value, weight, and zip, we zip them together, right? Using Python, it's really nice to zip the both lists together. Again, let me add this. Should be a list, right? List, right? And list. I think you can write this, or am I doing correct? Or list, or small list like this? Yeah, this like I forget. Yeah, type hints, and this will be integer, right? Int, right? Int, right? And what are we going to return now? What are we returning actually? Oh, knapsack, total weight, and I don't know what that else is. Knapsack is the object, right? Yeah, a list. So we return a list. Integer on integer for now, I guess. But of course, remember in Python, these are just type hints. I can't even do this. Oh, I can't even do this. Ah, because it's a tuple. It's a tuple, right? It's a tuple, right? Tuple. I have to do like this, I guess. Tuple, right? Yeah. Because remember, this is a tuple, right? This is a tuple. Okay, but that's just Python. Don't, I'm just cleaning up the code a little bit. So again, what we do is we sort by. So this is our. So here now that we have the value by weight, we can use that as our heuristic, right? Again, what's difference in heuristic and the algorithm, right? Heuristic is usually part of algorithm, right? Heuristic is like a rule, but it's not a full solution. It's just like it could be part of your solution, could be multiple. Heuristic is just a simple rule, right? You see a tiger, you run. You use the lowest price, right? It's some sort of problem, but it's not a full algorithm, right? So here, as a heuristic for greedy choice, right? So does we sort again? Team sort, right? Team sort is O log n, right? Complexity, right? So. Enumerate value by weight, right? And key value again. So this is the tricky part. This is why I don't like this code. It's not so readable. So this part here, what the heck is going on here? X1. What the heck is going on here? Do you know? Why am I doing this, right? What's going on here? That's why this code is kind of hard to read. Well, what's happening is this: we are enumerating, right, these values, right, value by weight, right, and we're using the value. The actual value is the value by weight is actually what we use for sorting, right? But we added indexing for this, right? So it's because of these original values, right? We need to find out which one is which, basically, right? We have pair value. We need to associate it with this value. With the originals, right? So we pack them together. We add original index to our values by weight. Okay. To get the weights and lists. Okay, but okay. Now we initialize knapsack. Knapsack is empty. So why do we use underscore? Again, Python question. When do we use Python underscore? Yeah, we don't care. Basically, it's just we have some number of values, right? We want a bunch of zeros, right? We don't know which items we want to take, right? That's our knapsack, right? Again, this really to make this code more readable would be make it more object oriented, basically in this case, right? This is just basically using lists, and this shows how if all you know is lists, right? Your code, again, you can do pretty much everything, but your code can get quite unreadable, right? So we don't even use any dictionary here, right? So total weight, because I didn't write this code originally, so this I would really want to rewrite. So for I insert index, right? We go to the best deals, right? And here's our rule, right? If total weight plus weights capacity, if we still can add, we start with the best bang for buck. And we keep going down the list, right? And we keep adding if we have the weight to do it, right? If our backpack still has room, right? So this seems like a good solution, right? this looks like greedy rule. I mean, it obviously seems reasonable, right? Best bang for the buck, right? So, and we'll see, does it always work? That's a big question. Oh, and I can't, what they do here, tuple, 3 arguments. Let's see, let's 1 second, what they do wrong here. Type error, return knapsack, total, this is list, integer, right? Maybe total weight, total value. That looks okay. Maybe a float somewhere. What's happening here? Maybe weight is float. Maybe it's a float, but what's wrong here? Capacity 1, 2, 3, 4. Where did I go wrong? Maybe this is, I don't know, I forget how to write this. Maybe this typescript, maybe I'll ignore it for now. I don't know, this is a Python issue. Let's do one more time. Yeah, okay, yeah. So the type hint, I forgot the return value, how to do this. It's a tuple, but it's a list. Tuple including the list. Weight, which is integer, and this could be maybe a float. Yeah, oh yeah, so list integer. So what are we returning here? So list integer, returning any literal, any literal, okay, yeah, silly. Okay, but yeah, so let's try it. So this is our example, this book example. So, as you can see, so in not a shocking example, we added this one first, right? Because this has $4 per kilo or something, right? This gives you the best bang of buck, and this gives you the second one, right? So now looks okay, right? You can do it again, debug, right? We add this one first, right? The best deal is the one with value to weight 4, right? Are you guys with me so far?
Yeah.
You can follow the rule. The rule is simple, right? Takes the best, which gives you the best money, per kilo. Now, but let's look at another example, right? And of course, now we'll get to some floats. So we have 70-40, right? 40-30, 34-20, right? So let's do some calculations. Yeah. So what I'll do is 40-70, still 50 capacity. So what gives you the best value? This one gives you the best value. So this will be the first one to be added, right? Right?
Yes.
Yeah. So do you see already the issue here, right? Right. So 70, right? The solution would give you only one item, 40 kilos, right? And you get $70. But hopefully you can see this with a simple math, right? What I could have done is, I could have taken second and third item, right? Fill out the bag to the full, 50 kilos, and I would get 74 euros worth of, value, right? Even though, objectively speaking, both items have less value. And again, so here's discrepancy. Or greedy algorithm, right, gave you the best bang, but since it's O1 problem, an abstract problem, O1 meaning we either choose or don't choose, right? It would have been better to fill out fully the bag instead of taking the best item, but then end up with some empty space, right? And again, of course, you can even just maybe make it like, it doesn't have to be completely full. I can maybe do even 29 probably would work, right? So, yeah. The problem is it suggests 40 weight and value of 70, right? We have gotten a weight value of 74 instead, right? So the greedy approach in this case, or one problem, actually an abstract problem, is extremely hard to solve fully. If you have a big O1 knapsack, actually, right? The greedy approach will not work, actually, right? So, but here's some good news. We can adjust this problem, right? Well, if we can, right? Assume, if you make an assumption that I don't know, it could be gold bars, silver bars, maybe butter, I don't know, or sand, right? They can be, of course, cut or taken partially, right? So-called fractional knapsack, right? You can take something, don't have to take everything, just a piece of it, right? So here's some good news for you guys. We'll see if greedy approach will work. So basically, the rules are different. we can include, instead of including, excluding, we can take something. So how will our program change? What do you think? Well, what's our approach? Do we change the value? You know, the best bang for buck calculation? Do we change that? Should we? I mean, we should still calculate it, right?
Yeah.
Yeah. But now what can we do? Now we have a big advantage over the previous problem. Let's imagine we take the best value, right? You know, the most expensive per kilo, right? We keep going. Eventually, so if our bag is small enough, right, we don't have enough room, but what should we do? We should cut the current item, the one which we are currently considering, right, which currently does not fit, right? Like, what's the story of, I don't know, not Snow White or whatever, they cut in original Grimm's, they cut the toe or whatever, those stepsisters. But yeah, but we cut it, right? It needs to fit, right? We cut it on problem solved. So this smells pretty good to me, actually, right? As a kind of why? Because at each step we're making the optimal choice. So this should be a very good solution. Actually, it turns out it is. The greedy approach here is the optimal solution. So if you have a fractional knapsack problem, right? Because at each step you take the best available choice, right? You take as much of the best value, right? So, I mean, this I think it can be very proven pretty formally that you, at each step, you are getting closer, you know, of maximizing this value, right? Of the most money you can bring in, basically, right? So knapsack fractional, the code gets a little bit messier. We can use the previous code, right? However, we need to add an else, right? So this is what I added, basically, right? So if less or equal, right? We still do that, right? We have enough room, we add everything, right? That one item, we add everything of that one item. However, if we don't have enough room, we check, right? So fraction, right? If total weight plus weight is less than available capacity. So here's the thing, again, if we don't have room, there's another beauty of this, right? Of this approach. How many items do we have to cut? One, because that's it by definition, right? We cannot cut more than two because, well, if we had enough room, we wouldn't have to cut it, right? We could just put it in, right? So at some point there's not enough room. It means we have to just cut one item, then we don't have to check it again. So this is kind of else, right? So here, right? So this part. So in this problem, we only need to cut one item, right? Yeah. By then the knapsack will be full, right? So allowed capacity, total weight, we know how much we have. Capacity and total weight, right? Capacity is what we were given originally. That comes in, right? That's our limitation. That's our optimization limitation, right? Our parameter, and that's what we have currently. So we do a fraction, right? We do some rounding, right? Maybe, you know, floating precision. That's just a technical detail, right? And then we add this, right? And also we calculate the value, right? We also need to know how much it costs, right? So we also need to calculate how much value we added by this partial addition, right? Okay. So now, right, we added this, right, the bug, and that's it. Yeah. So of course here, so this else, well, technically we could break even here, right? We are finished already. We could return already, right? But okay, right. So knapsack total weight round. So let's see a simple example. 20, 50, 30. This one does not change, right? Exactly same as before, right? Because if it's exactly, so there's no need to cut anything, right? Right. So now let's do 50, right? We can do it here. Weights and values, right? And we have capacity 10, so we add only 1/3, right? Small backpack, right? Okay. So now let's do this. So now we move on to this. Now this So now example. Now on to example. Example which failed with 0, 1. Failed to give to work in greedy approach in knapsack 0, 1 problem. Okay, so again it didn't work, so now it should work. So we'll start with this one. No, which one gives you the best money? This one is the most, 175. We'll take this one is 170, right? Yeah, 170. And we'll cut it a little bit. So we'll probably expect, what, 40 kilos of this and 10 kilos of that, right? And we're finished. Easy. I hope so. Yeah, half. So, yeah, half of, so one full item of 1.7, right? 0.5 of the other. Together, the value is $87 or euros or whatever, right? So, and again, it will keep working. So basically, again, because it's this one, you can do prove with induction that it's each step, right? Remaining, right? At each step, you want to take the best value per kilo per weight, basically. So does this make sense?
Yeah.
More or less, right? Yeah. So. We have like 10 minutes. Let's see, point cover, another problem. We want to find a minimum set of points so that each interval is covered at least once. Right. So, I think, remember this has practical application. It does have a practical application. Right. Sort of like we want to cover some things basically with the least amount of approaches basically. But let me see what, okay, yeah, again, problem scheduling lectures, right? Least number of classrooms, okay, that's again, who cares about that? Well, you don't care about this, scheduling in this regard, but of course, school administrators would care about this one, right? So, it would be more applicable if I was giving this lecture to school administrators, right? But, but still, least number of classrooms, right? So you don't want to, you have a big building, right? This could be actually quite important, actually, right? And again, also for, in the warehouses and shipping, manufacturing, and so on and so on, right? You want to utilize the least amount of machines, right? You have some manufacturing machines, right? You want to cover them all, right? So, so this is again a classic problem. So you have intervals, right? Right. So it's similar, right? So, values are endpoints, but is this actually same one? Actually, let me see this. Is this the same one before, or is it actually not the same one? I'm trying to remember this. Why is this actually a bit different? Well, there's some difference now, because previously we want to maximize the number of lectures. Here we want to minimize the points, which will cover all lectures. Yeah, it's different. Yeah, it is different. Yes. Okay. Yeah. Yeah. Points would be the classrooms, right? Least number. Okay, so points would be the classrooms. Intervals would be the lectures, right? Yes. Yeah. Sort intervals increasing order. Interval set. Interval not covered. Add interval endpoint to the set of points. Okay. So basically, again, log n sort, right? Intervals on. We have the points. Right? Start with 1 point, basically. Yeah, okay. Yeah. So, again, these are just generic times, right? Very similar. It's kind of similar to the first one, but it's not the same, not quite the same, right? So, 2 to 5, 1 to 3, 3 to 6. So, in this case, the solution, of course, is what? Well, we have two solutions, right? We want to have which point will cover all 3 intervals? 3.
Yeah.
3 also, I think 2 would cover, right? So actually anything from between 2 and... No, sorry, it's only 3, sorry, yeah, only 3. 3 is the only one, we assume the endpoints cover that, right? So in this particular case, the only solution is 3, yeah, because 2 does not cover this one here, right? So, yeah, this works. 3 works. So now we have 4, 7. So now we don't have full solution, right? We have multiple solutions here. We need 2 points at least, right, to cover the space. So 1, 3, 2, 5, 5, 6. So 1 to 3, 2 to 5, 5 to 6. So we have from 1 to 6, right? So 2 points. We need 2 points, right? We don't have any single solution, right? Because if you choose 3 here, right, not gonna cover the 4 to 7. So let's see what the solution is. 3, 6, yeah. Could be others ones. So 3, 5 would work, right? 3, 4 would work also, right? So this is again maybe a little more too abstract. I don't like this example too much, maybe because also I'm getting a little bit tired. So minimum points again, yeah, it will work, right? So I can try one more example, right? One more example. The single points equal. Maybe 10, 20, on I don't know 18, 25, right? On I don't know 11, 19. Okay. So obviously again we just need single point, and in this case, or maybe I don't know like 8. Okay, yeah, but you have 2 solutions, 19 and 20, right? Or anything between 19 and 20 if you allow floats, right? So midpoints should be 19, yeah? So you can see how it works. So again, so it works by, we choose, here we sort by intervals, we choose the ending point, basically, right? Yeah. So you can do a reverse, we can just do the starting point also, right? So again, in this particular case, it works. Pairwise distinct summands, not gonna look, but set cover, right? Minimum number of subsets, set of the unions contains all items in target set, universe, right? So you have a universe, 1, 2, 3, 4, 5, that's our universe, right? You have a collection of sets, right? 1, 2, 3, 2, 4, 3, 4, 4, 5, right? So this is a case where greedy approach will not give you the best solution, but it can give you close enough. So what's the solution we can use? While this is still not finished, we have not finished our set, right? We're collecting our Pokemon or whatever, right? 150 Pokemon, or how many Pokemon are there? I don't know. Anyone? I don't know. I have
1,000.
Yeah, something like pretty big set, right?
Yes.
Yeah. So while you still have some, pick a set that covers. So here's this is a greedy rule. Pick the set that covers the most of the elements. Right. So you still have some sets you have not checked, right? You pick the one which has the most elements, out of the covers most elements in U, basically, right? So again, it turns out this is a case where this is not the optimal. You will not find the optimal solution, but it can get you pretty decent solution, right? So again, greedy approach might be. Again, the lesson from this whole thing is you might not need the absolute best optimal solution, right? But if if it takes you like half the age of universe to calculate the most optimal, checking all the variations, right? So greedy approach can get you a solution which looks decent most of the time, right? You can check some edge cases, maybe see what's the worst happened, right? You're getting solution, things work. Then you can start optimizing. Maybe there's some things you optimize, you can cover these edge cases, right? So this is pretty interesting. So yeah, so let's see if this actually how it works. So you have a sets used, elements not covered, right? You have what is this? This is a set, right? We have some nice set operations. And we would like to basically end up with nothing, right? So these, while elements not covered, right? So while set is not empty, right? Elements covered is set, right? For set the collection keys, for each set is set used, continue on. You add a union with the current set. So the question is now, current set collection set would cover. Okay, and if this set helps, we just add new elements, right? Very simple, right? So let's take a look. So this works. So 1, 2, 4. 1, 2, 4, right? So in this particular case, you see it worked. But is this the optimal solution? Is it? Was this set needed, basically, the question is. It was not, right? Because we sorted basically, this is sorted by number of elements, right? Basically, so we added 1, 2, 3. We added 2, 4 because 4, we still didn't have 4 at the moment, right? I mean, it's helping at the moment because we had no information that 4, 5. The perfect solution would be 1, 2, 3, and 4, 5, right? Do you agree on that? Yeah. So this will be the best solution. Set 1 and set 4. Union of those two sets will give you the best solution, right? But again, using a greedy approach, you didn't have this information, right? And actually, in fact, we could not have it, right? It's a greedy approach, we can't solve it optimally, but we could have a solution, right? So it's up for you to decide whether it's allowable in your problem space to have some extra, some redundancy, right? Instead to, throw it out, right? And again, so this is tempting. Like again, eventually, if you want full solution, sometimes the best thing is to do brute force, check everything, right? And go back to. But then, of course, we will see there might be something better, right? We'll move on to other approaches. Move on from greedy approach onto other approaches such as dynamic programming. Maybe we can use some of this information to adjust our solution, maybe build a solution using some intermediate steps, some extra memory basically, some steps, some information about this problem basically, and build up the solution. But for now, greedy approach, it should have a simple rule, simple to implement. Again, I think for pretty much any problem you can figure out a greedy approach. It just might not give you the best solution, right? So yeah. So because again, like set problem is NP complete turns out, right? Which means it's basically involves there's no regular solution for absolute global optimum. You need to just check every possible solution. So for example, 2 to the 30, you need to have like million combinations, 2 to the 30th, right? For 30 sets, right? You need to check all of them. And of course that can get, 2 to the 30th is no big deal, that's 1 million. But 2 to the 60th, that's million times million, right? That's not so good, right? So that's trillion, right? And so on, right? Yeah. And again, in this particular example, we see that again, sometimes greedy approach, another takeaway from this, sometimes greedy approach will give you the best solution even to the problem which in general is not solved by greedy approach, right? Like we saw here. Maybe we can choose some things, right? So one approach, like in this particular example, right? You have sets, you can try, maybe, okay, you have like, 100 elements, right? 100 sets. You need to check. You can't check them all the combinations. But what you can do is you can try a greedy approach, but you can sort sets maybe a couple different orders maybe, and then check which solution is better, right? It's easy because greedy solutions generally run pretty fast, right? Because they're simple, right? You just run through. You can have 1,000 elements set, right? Which is completely infeasible to calculate. But you could run it like for a sort by the biggest, maybe adjust some parameters, maybe to add some little randomization. That's another tip. We'll talk about random algorithms. Sometimes a little shuffling. You can check maybe, because like say these 3, right? As far as this algorithm, they're exactly the same, right? 2, 4, 3, 4, 4, 5, right? These are just the, numbers don't mean here anything. The 2, 4 is just the identifier, right? You can shuffle them around. Maybe the randomness would give you a better solution, right? And you maybe check 4, 5 first, and then you don't have to check the set 2, 4, right? So that's another tip. Okay, so main takeaways from today's lecture. Greedy approach, you find some simple rule which solves this one step of the problem, and you break down, move on to smaller subset of the problem, and apply this rule again, until you have no problem left. You have 0, right? Nothing. So maybe we'll do some greedy, we'll try to solve some problems maybe in midterm using greedy approach. Maybe. Yeah. All right. Any questions? No questions. Okay, so we meet.